Good morning, everybody. In honor of actually keeping on time, we're just going to give you a couple heads up. We have the timer set for 14 minutes, so it's going to start flashing yellow at you at 11 minutes, just to be able to have time for transition and questions. So we're going to get started. Our first speaker is going to be Roderik.
Well, thanks for inviting me to be here. I will give a presentation on sea level allowances along the world coastline. It's work which I do together with some people at IMO in Utrecht, Christos, Thomas, M.A. and Renske, and some two foreign collaborators, Sanne, Muis and John Hunter from Tasmania, and Sanne is from Vrije University. Oh, that was two. So how do we calculate sea level changes? I think the most important thing to realize is that we make a distinction in two parts, mass changes and volume changes. And mass changes is all which is related to ice and terrestrial water changes, so glaciers, surface mass balance and ice sheets. And that is needed because we have to calculate fingerprints for those contributions in order to find the relative sea level distribution over the entire ocean. And at the same time, we have volume changes, which is mainly the steric component. Dot. And if you add those together, you end up with a distribution of the regional patterns of sea level change over time. And if you use the CMIP5 data as input, you can calculate for the next century. And that results in patterns like you see here. In the left column, you see this results for RCP 4.5, and the right column is for RCP 8.5. The upper row is the glacier and ice sheet contribution pattern, and the second row is the steric component, the GEA component, the third one, and the fourth row is the total sea level projection for the two different scenarios. And you can clearly see the fingerprints of the ice sheets in the upper row, and the more detailed pattern of changes caused by the steric component in the second row, and that's what you see back eventually in the last row, which has the total sea level projection. And you can see that basically the pattern of 8.5 is an amplification of 4.5. But that is a pattern which has in fact the mean over time in the trend, and secondly, it is very important to consider the distribution of the sea level trends, and that is illustrated in this graph, where you see, for instance, the RCP 8.5 without ice dynamics in the blue curve, and if you add ice dynamics, which in this case are taken as a skewed distribution, which is a kind of tendency we see nowadays in sea level projections for ice sheets, you can clearly see that the mean is changing only 14 centimeters, whereas the 95th percentile is changing about 32 centimeters. So it's very important, if you are interested in small chances, to consider also the distribution of the sea level trends. And that is what you see in the next graph, where we have calculated the percentiles of the sea level contribution, the 90% percentile, the 95% and the 99th percentile, and in this case for a given certain asymmetrical distribution of ice sheets. And of course you see a strong amplification in the areas where the fingerprints provide you a very high sea level, so that's far away from where the ice mass change takes place. But this is all about trends. And that's not going to be enough if we make sea level projections anymore, because there's much more, and that's where we get to hear about also much more in this session. There are also extreme sea level changes, and there are many processes playing a role eventually in the water level which we experience at the coast. Many processes, first of all these processes work on different time scales, and they work also on different spatial scales, and that eventually makes up what happens at the coast, and it's clearly insufficient to have only a projection of the mean sea level change, because that is not what eventually determines the flooding risks. So we somehow have to combine projections of the mean trend and the extreme sea level. And just as an illustration of the variability, here you see 4 records of tide gauges, Barcelona, Delfzijl, Caltech, and Willapie Bay. And you can clearly see that they have a very different signature, which we somehow have to acknowledge. And the first step how we could do that is by calculating a Gumbel distribution over this tide gauge records. And you can clearly see in this case that the Maldives has a very narrow peak, so this results in a very small scale parameter, and Delfzijl has a lot of variability, so you have a very large scale parameter in your Gumbel distribution. So there are enormous differences from side to side. And this has to be taken into account somehow, and we do that in this case by the concept of allowances. And I guess not everybody is familiar with the concept of allowances, so I've written down a full definition of it. But it's basically the height you have to raise a dike to keep the risk of flooding identical to what it is now. And if you follow the Gumbel distribution approach, you get a very neat and simple equation, which is written down there, where you can see that the allowance is the sum of the relative sea level change plus a second term. And the second term is determined by the uncertainty in the sea level projection and by the distribution around the mean value of your, in this case, tide gauge record. And as all those parameters are positive, it means per definition that the allowance is larger than the relative sea level change. And it also shows you that areas which have a large Gumbel parameter, skill parameter like Delfzijl, are less vulnerable, so it means that the allowance is closer to the mean relative sea level change. And areas where this is not the case, there the allowance may differ quite a bit from the trend projection. Of course, this is disputed how you should do this, and I guess that Thomas will discuss this in more detail in one of the later talks. In the Gumbel distribution, you have that the water level as a function of the return period is completely linear, and there are many locations which do not show that behavior, and for that reason you may want to use other statistical distributions. But as the mathematical analyses are simply, if you do a Gumbel distribution, we stick here to the Gumbel distribution. And we can calculate, based on the tide gauge data set, the Law Dataset, the allowances everywhere along the coast where you have a tide gauge. And that is what you see in this graph here. And the left graph gives you the allowance, the middle graph gives you the difference between the allowance and the global mean IPCC projection from AR5, and the right graph shows you the allowance minus the local mean sea level. So this was published in a paper in 2017 by M.A. Slange, and this is the first step you can do, because you have a reasonable insight in the variability based on tide gauge records. But that doesn't provide you data everywhere, and in order to do that, we have taken advantage of progress in hydrodynamical models. This is work from Sanne Muis, and she will discuss this in more detail later. But you can calculate on a global scale the variability of sea level based on meteorological forcing, and that provides you a time series, and that provides you also, if you apply some extreme value statistics, eventually scale parameters along the entire coastline of the world. And that is illustrated in this graph. This is a little complicated. 9 different locations. The lines are the allowances, and the curves are the relative sea level changes. And if you look, for instance, to San Francisco, hang on. We first have the colors. Red is the tide gauge allowance, and green is what the model does. So red and green in principle should overlap. This works reasonably well in many areas, except in the areas where tropical cyclones are important, and that will be addressed by Sanne in a later talk. And so, like for instance in New York, the model works perfectly well. There is no green line visible, so green and red are overlapping, and the model does exactly the same as what the tide gauges suggest it should do. And there are also some regions where it works not as good, like Pago Pago in the right lower corner, and the Bay of Bengal is also not the perfect one. But there are many locations, as long as you're not too close to the tropics, where this works pretty well. So the advantage of this approach now is that we can calculate the allowances along the entire coastline, and here you see a result for Europe, where the lower graphs is based on the Law Dataset, so the tide gauge data, and the upper graphs gives you insight in the allowances along the coastline of the entire European continent based on the GGSR hydrodynamical model, and combined with the relative sea level changes from Slangen et al. Of course, there are many factors determining the variability, and one of them is the wave height. And what we attempted also is to include the change in the wave height based on the co-clip work, which is basically about 8 GCMs which calculate changes in wave height over time. And what we did is that we added the change in the wave height over time as an additional component to calculate the allowances. And what you can see here in this graph is the change of the mean wave height over time between present day and a future run. So green means an increase in the wave height. So the Southern Ocean is expected to have higher waves. And you also see this in the Bay of Bengal and near Bangladesh. But you also see areas, coastal areas, where this is lower. And these are the red areas. So this is what we used in addition to what we already had in order to calculate allowances. And that is what you see here. And for the same 9 areas, you can clearly see that there are few areas where, in fact, the allowance is completely determined by the waves, like in the Bay of Bengal and in Pago Pago. The wave contribution is very high, and there are also areas where this is absolutely not the case, like, for instance, New York. And on the other hand, we have areas where the allowance is deviating quite a bit from the mean projection, and there are areas like IJmuiden where the variability is already high, and as a result allowance is small with respect to the projection, and there the complete story is basically determined by the relative sea level projection. So we have now a lot of possibilities to address sea level changes, much more than we had. And for instance, the end result you eventually have is shown here, where you have the GGSR allowances in the upper graph and including the waves in the lower graph. And if you look at, for instance, then again in the Bay of Bengal, you see that there the difference is pretty large. So the projections in the past, we had global estimates, and now we can do the regionalization. We can add a quantification of an isodynamical component in a kind of statistical way. As a result, we can calculate probability estimates, and we can also say kind of first word on projection of the extremes. With respect to the extremes, I think we can include them now. We still may have to work a little bit on the extreme value statistics, how we should do that in the best way, given the fact that tide gauges show that we should do it in another way than what we did in the model. And of course this is very important because if you look to flooding frequencies, around 80% of the world coastline will experience a 1,000-fold increase in flooding, so that's quite significant to work on this. We have to realize that the change in the variability is not really captured here, only the effect of the change in the waves, but the rest of the variability is kept constant over time, and that may not be good. And of course, all depends eventually on what you precisely do with the ice dynamics. That's it. there's time for a quick question if there is one. Thomas?
Just to clarify, the 1,000-fold increase, is it flooding frequency or extreme sea level exceedance frequency?
Exceedance.
Okay, so areas like the Netherlands which do not flood now may still not flood, but the certain thresholds are exceeded much more.
Yeah.
Okay.
Okay, let's move on to our next speaker. It's Sanne Muis. Okay, I knew I'd butcher that. I apologize. We need to switch the screens here to PC. There you go. So this is an invited talk, and Sanne, I think, is going to continue on that thread, the extreme sea levels, considering the cyclones.
Yes. Yeah, so today I'll present some work on the modeling of extreme sea levels at a global scale, and also try to see how we can include tropical cyclones at a global scale, which are a key component. I've been working on this work for the last year, and it included a visit to Princeton University for a couple of months where we tried to include the tropical cyclones. So as you all know, areas around the world experience devastating impacts due to flooding, and tropical cyclones are in many regions the key driver of extreme sea levels, which can result in large damages and floods. And due to the increasing risk, both due to socioeconomic development, but also climate change and rising sea levels, changes in storminess, there's an increasing need for accurate information at the global level. So where previously most hydrodynamic models were applied at a regional level, and on global scale modeling was more focused on mean sea levels, we actually need also projections of extremes to assess risk. In the last few years, there have been several advances, and we have been able to apply a global hydrodynamic model, which was made possible due to increasing availability of global data sets like bathymetry, elevation, but also climate reanalysis data. Improved hydrodynamic algorithms, so the global model that we use implements in structured grid, so flexible mesh, which allows to locally refine the grid and use the computational power there where we actually need it along the coast. And in addition, we have increasing computational resources which allow to run this model at that scale. So a little bit more information about the work that we did. In 2016, we published a global reanalysis of tides and surges. Storm surges were modeled with a global tide and surge model, which was forced with ERA Intram. At that time, tides were not fully included in the model, but at the moment it is. So at the moment we can run it simultaneously. But at that time we used the FAST 2012 model to model tides, which we then simply added to the storm levels. The dataset provides time series of surge, tides, and total sea levels along the coast. And in addition, we assess the extreme value distributions along the coast. And it was actually the first global dataset that's been based on the hydrodynamic approach that provides sea levels along the coast. And we spent a long time on validating the modeling, trying to find out where do we actually perform well and where do we still need additional resolution or better methods. And we provide time series at a daily time scale. So this is a graph showing the model grid. And as you can see, the resolution increases towards the coast. Along the coast, the resolution is about 5 kilometers, and in the deep ocean, it's about 50 kilometers. And then we force it with ERA Intram data. And this is showing the validation of the time series using the sea level dataset of Hawaii. And as you can see, this is showing the correlation coefficient of the daily maxima. And there's a good performance in many regions around the world, but especially in tropical regions, we see the performance is less accurate. And the main reason for this is that tropical cyclones are not fully resolved by the coarse climate models that are underlying ERA Intram. So they are there, but their intensities is not fully included. So we underestimate extremes in the tropical regions. At the same time, they are responsible for the most damaging storms at the global scale. So there's a clear need trying to address this issue and trying to see if we can get a better estimate of extremes in tropical regions as well. And to do this, we need higher resolution forcing. So one goal was trying to see for the Atlantic, how can we fully include tropical cyclones and develop a data set that does not only include the extratropical storms, tides, but also these tropical storms. And to do this, we explicitly modeled the TC winds using a parametric model, and then combined these tropical cyclone surges together with tides and results from ERA Intra. So this was the model framework that we used to develop the global reanalysis dataset. We modeled tides and we modeled surge levels driven by ERA Intra. But now as a next step, we also include a hurricane wind model. So we use tropical cyclone track data, EB track in this case, which provides the location and the characteristics of tropical storms from 1988 to 2015. Then we fit the Holland parametric model to a high-resolution grid, and then force the global tide and surge model with this forcing. In the end, we combine the surge level by taking the highest surge at each moment in time. It's just a bit of a simplification, but it's at the moment the best approach, I would say. And then again, we add tides to get to the total sea level. Yeah, so in this case, we applied it to the Atlantic. The main reason for this is that there is much more data available for validation, and the best track data in the Atlantic also includes the radius to maximum winds. While the IB track dataset, which also provides tropical cyclones at a global scale, we will need to do an estimation of this radius, which is possible, but for now we decided to do a detailed analysis for the Atlantic. So this is some results of the wind forcing, mostly just to show the severe underestimation of the wind in ERA Intra. So in the left panels you see the wind fields for Katrina, and the upper panel showing the wind fields for ERA Intra. The one on top is EB track, so that's based on the track data fitted with the Holland model. And below you see the H-wind dataset, which is a detailed wind reanalysis and sort of a good estimate of the actual wind field. You can see that there's a severe underestimation in ERA Intra, and while EB track's not fully capable of getting at all the more complex storm, so especially as you can see for Irene and Sandy, when the tropical storm was transitioning into an extratropical storm, we overestimate the structure of the tropical cyclone. And it also has some difficulties getting the asymmetry right, but at least the intensity is much better represented. And in the next graph, you can see this also results in much better representation of the surge levels. So again, Katrina, Ike, Irene, and Sandy. And therefore, I think for Katrina, EB track resulted in a maximum surge height of about 6 meters, while in ERA Intra was maybe 2 meters. So there was using this parametric approach, we're much more capable to model these tropical storms. And we see a really large improvement in the model performance. At the same time, it's a global model, so the resolution is limited, especially in estuaries and in regions that have more complex dynamics. For example, if the barrier islands only have an opening of maybe 1 kilometer and our resolution is 5 kilometers, we won't be able to capture those processes. But we are able to get a good picture of the spatial distribution of the storm surge and assess risk at a large scale. So would not use this for regional applications, but if you look at large scale risk dynamics, we're capable to get the main dynamics. So much better performance for the surge simulation that are based on the best track than those based on reanalysis. In the case of Katrina, the correlation of the maximum surge height increases from 0.77 to 0.95, so it's a good measure. And for the other 3 storms, we see similar improvements. Yeah, and we see that the spatial pattern is coherent with the observations. But at the same time, there are some regions where we're not able to capture those things. So this graph is showing the observed surge height and the modeled surge height. And to do this, we used all observations that are within 250 kilometers of the tropical cyclone track, and then take the maximum surge that occurred in that time. As you see, there are some extremes that are not being reproduced by the model. In some cases, this is because it's outside of our wind field, or it's behind some region that we're not fully resolving. But as a next step, we combine it with ERA Intra, and we see a much better representation. So here we used the highest search height at each moment in time to combine ERA interim and the track data. And you see especially that some of the underestimation of some storms is now removed, although there's still some bias, but it's mostly within like a reasonable amount of error. And then as a next step, we combine this with the tides. And we also see a good, so in this case we used peak over threshold and used for each location 3 events per year, the highest 3 events. And I looked for that same, for the corresponding modeled search total sea level. And we see a good representation of in the model. So what's next? Well, now we have like a historical time series for the last, from 1998 to 2014, which may be useful to analyze what are the drivers of extremes or what's the spatial extent of certain events, but cannot be used to assess risk because we need probabilities. And in those 20, 30 years of data, there are not enough tropical storms to estimate these probabilities. So in the end, we'd like to try to couple the model framework with synthetic tropical cyclones track to really see if we can get a map of probabilities of extreme sea levels in the Atlantic. But because we use a global model, it's also easily to extend to a global scale. We've run the global model also with EB tracks, so we have a lot of data, but we still need more time to see what we can to analyze this. Then a summary. Yes. So we have the global tides and search reanalysis data set, which provides 36 years time series of extremes. Then we fitted gamma distributions, which are freely available, so if anyone is interested in using them, just send me an email. And we see a slight underestimation of extremes, driven by the resolution, mostly of ERA interim, and this is particularly problematic in tropical regions which are prone to tropical cyclones, which require much higher resolution. So then for the Atlantic, we try to assess this issue by specifically modeling tropical cyclone winds and combining them with ERA interim and tides to develop new time series. And it shows that the model is capable of capturing this large-scale variability in extremes, although there are some issues in more complex regions. And future research directions include coupling the framework with synthetic tracks, but also expanding this analysis to the global scale. Thank you.
There is plenty of time for questions. Over there. Can you repeat?
50. Yeah. So he's asking the resolution in the ocean. It's about 50 kilometers. Yeah, so the resolution is mostly depending on the depth. So the resolution will increase towards the coast. So in the deep ocean, it may be 50 kilometers, but will already be much more fine, coming closer to the coast.
Questions? Detlef?
Thanks for this nice talk. But I do have a question. Is this just sort of an analysis or looking how this looks like, or do you want to go to a prediction system where you have a data bank and once there is a tropical storm and you see the trajectory coming, that you also can actually do predictions of what specific regions might experience?
Yeah, so the global tidal search model is also running operationally. This is done by Deltares. It's called the Glossus model. So they use the ECMWF global forecasting system to, so the models run 6 times a day to provide this forecast. And I think, yeah, actually those forecasts have a better resolution than ERA interim, so they're better capable of modeling these tropical storms.
More questions?
Did you run into any issues comparing your model results to the observations? Because we know the time cages are often knocked out because of peak versus slow observation. Is that something that maybe, that not your model is going bad, but comparing your model maybe to not the most accurate in situ observations? Have you checked that?
So I spent a lot of time trying to get the observation in a format where I could actually use it. And sometimes I think the observations are wrong and the model is better, but how it's difficult to.
Maybe you will expect soft data, high water marks that are not just high gauges. There's not a lot of information that could at least give you a better idea of what the peak might have been if the high gauge is not recorded.
Yeah, I tried looking into other data, but often it was difficult to compare it to the same vertical datum. And yeah, but in addition to the observation, we also compared to regional models, trying to see if we capture the spatial pattern. But
okay, thank you. We'll move on to the next talk.
So our next speaker is going to be Andy.
Good morning. I'm afraid Stefan couldn't be with us today, so you guys are stuck with me for the next 15 minutes. I'm going to talk about, we're going from the global scale to the extreme local scale to think about how relative sea level, tidal range, and extreme water levels have changed in Boston Harbor since 1825. We're looking at a picture here. If any of you have been to Boston, this is the Charlestown Naval Yard, the dry dock that was built there for ships to come in and be repaired, and it's a site where a lot of tidal measurements have been made through time. So the motivation for going back to try and get older data out of, I should say that this data is available in paper format in archives, which needs to be pulled out, digitized, and processed. And the motivation is really a threefold. If we have systematic water level measurements through time, we can use those to derive relative sea level trends, which is what we'll focus on today, really because that's where my interest lies. Stefan's interest is in tidal evolution, so we can look at how tidal ranges change through time and perhaps learn something about why that's taken place. And we can look at individual storms, extreme water levels, which in Boston are primarily driven by nor'easters rather than hurricanes. And we can get an idea about whether the frequency and the magnitude of these kind of events has changed. On the relative sea level side, we know that the distribution of tide gauge data is strongly biased in space and in time. We're looking here at the location of tide gauges in the Permanent Service for Mean Sea Level database that have at least 100 years of data. And it's skewed, obviously, towards northwestern Europe and towards North America. There are 12 locations in North America with more than 100 years of data, of which 6 are on the US Atlantic coast. So it may seem unusual to look at Boston to try and extend that data when obviously we might want some from underrepresented regions, but by getting long data close to places we already have some data, we can start to compare and contrast to learn about process. So this is the Boston sea level record as it stands from NOAA, available from the Permanent Service for Mean Sea Level. It starts in 1921. It's a pretty complete record, goes through to present, and it records an average linear rate of rise of somewhere on the order of about 2.8 millimeters per year of rise. So what we want to do is to see if we can go back into these documentary archives and extend this record to pre-1921. And it turns out we can. The history of water level measurements in Boston Harbor begins with this resolute-looking gentleman, Leonie Baldwin. He was a civil engineer, born in Massachusetts, attended Harvard, and one of the things he did during his career was he was commissioned by the US government in order to construct dry docks at the naval yards in Charlestown, which is just on the north shore of Boston, and also down in Norfolk, Virginia. The first thing that Baldwin did when he started this project, civil engineering project, was to start to systematically measure water levels, because he wanted to ensure that the dry dock was built with a very specific relationship to sea level. He wanted it to be high enough so that water didn't come in during large storms or at high tides. Obviously, you want your dry dock to stay dry. So he measured the tides, began those tidal measurements from 1825 to 1827. Those data are available to us. We can find them in the archives at MIT, and also bizarrely in the Harvard Business School is where a lot of these papers have turned up. The photo is an example of a set of measurements from October, November, and December in 1826. And Baldwin used these 2 years of observation to define a datum that he called ordinary high water. It's the high tide, it's the height reached by 2/3 of high tides. Importantly, it turns out it's not the same as mean high water, which some other people have previously thought that was the datum that Baldwin was using, but some of the personal papers in the archives tell us that isn't the case. He then designed the coping of the dry dock specifically to be 5 feet above that ordinary high water datum that he defined. What it means is that the dry dock at Charlestown meets all the criteria of being an archaeological sea level indicator. After Baldwin made his measurements in order to establish that datum and design the dry dock was built, and tidal measurements continued at Charlestown by various different organizations. The US Coastal Survey, the US Navy, all made measurements at different times. What we're seeing in the little map here are locations of different tide gauges and different types of tide gauges and when they ran. So we have things like tide staffs, box gauges, but fortunately for us, all of these measurements were always referred back to the coping of the dry dock. So we can tie measurements from the tide gauge that ran from 1857 to 1860 to those from Baldwin's earlier measurements. In fact, one of the benchmarks on the dry dock still exists today. Benchmark number 2 is in the National Geodetic Survey database. So we're able to combine all these data sets pretty readily. When we do so, what we end up with is a record of relative sea level change, which goes back to 1825. The blue data on the recent end of this plot is the NOAA tide gauge data beginning in 1921, and the red data are years for which we recovered archival data. So the Baldwin measurements are the early ones, and there's a little break, and the US Coast Survey picks up the measurements, and then the US Navy, and the series shown in white are a set of measurements made by the Metropolitan Sewer District at a site called Deer Island, which is a little bit further out in the harbour. But again, those measurements were referenced back to the coping at the Charlestown dry dock. So of the 192 years, we have 145 years with data where our criteria for inclusion was we had to have at least 4 months of measurements. And if we apply a simple method to look for changes in the rate of rise, change point analysis, we can see that with 95% confidence there is an increase in the rate of rise at some time between 1916 and 1932, shown by the shaded envelope. So what about causes? What caused this sea level change? Well, one of the things we did was to compare the new extended record from Boston, shown in yellow in the top panel, to the existing data set from the battery on the southern tip of Manhattan in New York City. And we can see that through time that they diverge, which we would expect to be the case because of differences in isostatic adjustment between the two sites. The lower panel with the red data series shows the difference between the Boston and New York records, and for reference we're seeing a line there that is 1 millimeter per year of difference, but it's not we can see that there are times when the difference is a little bit faster than 1 millimeter per year or a little bit less than 1 millimeter per year. So if GIA is obviously a big driver of sea level change at Boston and at New York, what is the contribution from it? So what we're seeing here are estimates of land level change in Boston on the x-axis and in New York City on the y-axis, where the symbols represent different methods that people have used to try and estimate that contribution. In green we have Earth ice models from Dick Peltier. The yellow diamond is a spatial temporal model analysis done by Bob Kopp. We have some late Holocene sea level data from Engelhardt and Horton, which is a pretty dense network of data on this coast. GPS data from Crago colleagues last year, and then the NOAA tide gauge analysis done by Chris Service. So we can see in all cases we have a faster rate of rise, a faster rate of land subsidence in New York than we do in Boston. And the pink shaded envelope is data from Chris Picuch and colleagues that he presented in yesterday's GIA session. What Chris has done is taken all these different sources of data about land level change, put them into a single probabilistic framework, and he kindly computed the difference for us between land level change in Boston and New York, and he estimates it to be 0.71 plus or minus 0.32 millimeters per year. That's a 1 sigma range. So the observed difference that we see between Boston and New York of about 1 millimeter just about fits within that range. So if we detrend both of the sea level records, the Boston data and the New York City data, Boston now shown in red, where the light pink data is the annual series, and the solid red line is a smooth decadal type series. Same for New York, and we've added for comparison the global tide gauge record of Church and White as well. If we can see that the trend through time is one of rise, particularly since the early part of the 20th century. There's good agreement between the global tide gauge record and Boston and New York after we back out the contribution from GIA. And if we zoom in on the inset panel to the annual data between New York and Boston, we can see that there are years when there's very good agreement in the annual sea level variability between the two locations. That gives us some confidence that the data we've extracted from the archives is accurate, but we can also see that there are odd years when the New York and Boston series run in the opposite direction, and that's something we're still working on. One of the things we'd like to do is to go back to the New York City, very early New York City data and double check some of that. So I wanted to quickly finish on a note about this gentleman, John Ripley Freeman. He was a civil engineer, MIT trained, who was designed and built the Charles River Dam and also the sewage and water system in Boston and New York. One of the things that Freeman did during his career was he was interested in if Boston was subsiding and by how much. So he actually accessed some of this early Baldwin data and started to process it and do calculations. And he came to the conclusion that Boston was indeed subsiding, and in 1909 he was called to testify in a court case about land ownership in Boston Harbor. So on the inset map we can see a historic map of Boston where you can see the downtown shown in the pink, and then off to the north and east you can see a little island called Noddle's Island. Noddle's Island is now underneath Logan Airport. Noddle's Island had been granted as a colonial land grant. Subsidence was obviously making the island smaller, and the court case was about how far offshore land ownership extended. So Freeman testifies in court that tide gauges indicate that subsidence in Boston within the past 35 years has been somewhat more rapid than in the previous 35 years. This was in 1909. And Freeman was looking for a cause for the subsidence and was in touch with scientists at Harvard and Columbia and other institutions, and they could find no cause for this, although it was postulated that perhaps it was caused by a different amount of water being stored in the form of ice. We would argue perhaps that what Freeman was seeing wasn't an acceleration in the rate of subsidence. What he was seeing was a linear rate of GIA over this relatively short time period, but with the addition of sea level rise beginning during his lifetime, which perhaps makes him one of the earliest people to have observed the onset of modern sea level rise, albeit that he may not have known it at the time. So to conclude, we've extended the relative sea level record in Boston back to 1825, which makes it the longest tide gauge record outside of Europe. Importantly for people in Boston, it's now longer than New York, which always matters. We've seen about 30 centimeters of relative sea level rise since 1825, of which about a half was caused by GIA, with an acceleration beginning in the early 20th century. That acceleration is consistent in timing and magnitude with global trends, and Freeman may have actually been one of the earliest scientists or engineers to observe the onset of modern sea level rise. So I'm happy to take any questions you might have.
Are there any questions? Back there.
Yeah, I noticed you excluded projections in, at the Norfolk Naval Shipyard, which, by the way, is not in Norfolk, it's in Portsmouth, as opposed to the Portsmouth Naval Shipyard, which is in Maine, just a historical note. But is it because of the problem with subsidence in the Norfolk area?
I'm sorry, I couldn't hear the question.
Okay, I'll try again. My voice is going. I noticed you left out trying to extend the record in the Norfolk area. Is that because of problems with different rates of subsidence in the local?
So the question was, why didn't we extend the Norfolk tide gauge record? Just manpower, to be honest. So Stefan has recovered some of those. So Baldwin actually built 4 naval yards: Boston, Norfolk, Pensacola, and Portsmouth, New Hampshire. So those data We have recovered some of those data and taken photographs of them. They just haven't been digitized, but there's no reason why it couldn't be done. And certainly I know Stefan has data from Norfolk that he recovered from the Naval Archives in DC.
Another quick question? If not, let's move on. Thank you.
All right, our next speaker is going to be Thomas, talking about analyzing extreme sea levels for broad-scale impact and adaptation studies.
Well, thank you very much. Okay, I will do things a little bit reverse today, starting with my references, because I really want to acknowledge all those co-authors who have helped me a lot, especially with those first two papers, where most of the results that I will be presenting today come from. The third one is a short perspective article that I recently wrote for ERL, where I tried to link the work that I'm presenting today to other work that has been done by other people recently on this broad and important topic of extreme sea level analysis. Now, thanks to the very important contributions of many of you in the room, including the people here to my right, we have developed a much better understanding of the different processes that are contributing to sea level rise. We have a better understanding of the temporal and spatial variability, and we have come a really long way from, in the first IPCC report, having a global mean sea level projection which ignored many of the important processes, or they were approximated very roughly, to something like this that was taken from Mark Carson's paper based on his work and Amy Slangen's work, where we are looking at relative coastal sea level rise projections. And we have a better understanding how the different processes contribute to these changes along the coast. And that is really what we want to use in large-scale impact and adaptation studies. The question is, how can we integrate this information in these kind of analysis? When we talk about flood risk, at some point we have to deal with extreme value analysis. Roderik already talked about that. And what we typically do is we use observations, or if we do not have observations, we use model output, like the one that Sanne talked about. And then we have to apply extreme value analysis. We have to fit some kind of parametric theoretical distribution to the sample of extreme events that have been observed or modeled for the past. And here I use the GEV distribution on the right-hand side as an example. As we saw earlier, at the global scale, the Gumbel distribution has been very popular. It's a simplified approach. But in any case, what we do is we fit this distribution, and we have to fit this distribution because we need to extrapolate beyond the length of the observational record to estimate return levels for return periods that are longer than the observational, than what is covered by the observational period. And that's very important because when we perform flood risk analysis in many areas, especially in Northern Europe, in other places where protection levels are relatively high, it is those high impact, low probability events that really determine the flood risk under present day and also under future conditions. So what we do is we then define some kind of sea level rise scenario that we want to take into account. And at this stage, we typically acknowledge that even though we have gotten better in projecting future sea level rise, there are still significant uncertainties. So we very often use different scenarios that are associated with different emission RCP scenarios, or we just stick to one RCP, but then we have multiple climate models, so we still have a range of uncertainties for this particular RCP of how sea level rise may play out in the future, and we take that into account. And then we modify the extreme sea level distributions that we have estimated before. So what's happening here is we acknowledge that there are still uncertainties in future sea level rise projection, but we implicitly assume by doing this that we have perfect knowledge about the statistics of extremes under present day climate conditions. And that's problematic. There are two key uncertainties associated, especially with broad scale, talking about global extreme sea level analysis. The first one is, even though the spatial coverage of observations has improved, especially with the recent development of the Gessler-2 database, there are still very, very long coastline stretches where we have no observational data available. So we have to apply models, such as the ones that Sanne talked about, hydrodynamic models, which we use to generate water levels for the past 20, 30, or 40 years,
and then we use that data for the extreme value analysis in addition to the observations in order to obtain full global coverage. The second type of uncertainty comes from fitting this distribution. As I said, we very often assume and pick one particular distribution at global scale, often the Gumbel distribution. We fit it to the data and then we modify it according to the sea level rise scenarios. And as I said, that's very important because we have to extrapolate to these rare events. So it's important for us to find an appropriate distribution to describe the sample of extreme events that we have available, either from observations or from model hindcasts. And here we are looking at the same figures that Roderik showed. So the IPCC, when they estimate uncertainties in sea level rise projections associated with certain RCPs, they run a bunch of climate models, 20-something climate models, and then they fit a Gaussian distribution to estimate the range of uncertainties, a 5 to 95% range of uncertainty in the future mean sea level rise projection. So what we did here to assess this, what I call type 2 uncertainty from the extreme value analysis, we did a very similar thing. We applied 20 different extreme value models to observational data sets. We started with the simplistic Gumbel approach using annual maxima. We used the generalized extreme value distribution with annual and monthly maxima. We used the R-largest method. We used peaks over threshold with a generalized Pareto distribution. And we can see that the range of results is pretty large in many places. The top left is an extreme example which shows us how the Gumbel distribution can be a very poor fit when we look at the observational data. And actually we found from looking at over 500 tide gauges that in most cases the Gumbel distribution would overestimate the return water levels. Now, from having this range of results, we can do the same things that the IPCC did. We can fit a Gaussian and get the 5 to 95% range of uncertainties in extreme sea level estimates under present day climate conditions. And that's what we are looking at here at the top. For the 100-year event, the 1% exceedance probability per year, because it's such an important event when we talk about defining flood zones, for example, or it's included in many of our design approaches. And at the bottom, for comparison, we are looking at uncertainties now for future sea level rise projections at the end of the century, here for the RCP 4.5 scenario. And we can see for many areas, the uncertainties in the future mean sea level projections are larger, are dominant over the uncertainties in the extreme sea level estimates. But we can also see at the top figure, in many of the high-risk areas, Europe, east coast of the United States, Southeast Asia, the uncertainties in our present-day estimates of extreme sea levels are already as large or even larger than the uncertainties in future mean sea level projections. And that's this type 2 uncertainty that comes from using different extreme value models. Turning to the type 1 uncertainty, the uncertainties coming from using storm surge models. I will go through that real quick because we've talked about it before. In this case, we were able to compare the results that we obtained from in situ observations at the Gessler 2 tide gauge locations with the results that we obtained from modeled water levels, and then applying the extreme value analysis to these modeled water levels. And we have two global extreme sea level data sets available. One is the Dynas Coast data set that has been used for the last 20 years, was developed a pretty long time ago, with a very simplistic approach. For how simplistic it was, it's actually surprising how good it captures the spatial variability of extremes. But if we look at the top figure, and again that's for the 100-year return water level, we see a lot of blue, and blue means that the Dynas Coast extreme sea levels overestimate the actual extreme sea levels, the ground truths that we derive from in situ observations. The second model data set that we can use for comparison is the GTSR data set that Sanne talked about a lot. In this case, we see a lot of red. So that shows us that GTSR has a tendency to underestimate the extreme sea levels. But if we look at the PDFs, and blue here is the Dynas Coast data set, red is the GTSR data set, we see how GTSR has been a huge improvement in developing more accurate global extreme sea level data sets. The PDF is much narrower and the median is much closer to 0, but there are still areas where the differences are pretty big. I would assume if we used the new version where tides are fully coupled with the storm surges, we probably see further improvement. but nevertheless, it remains to be a model. So there are still some uncertainties involved in that. So what we can do then is we can combine those type 1 and type 2 uncertainties from estimating extreme sea levels for present day with the uncertainties of future mean sea level projections. And that's what we did here for different return periods. Top is the 10-year event, bottom is a 100-year event. In the paper we also show the 1,000-year event because it is very important for flood risk assessments in many areas where protection standards are relatively high. Now for the 10-year event at the top, we see a lot of green. Green means that the uncertainties in mean sea level projections for the future, the end of the centuries, are much more important and larger than the uncertainties of the extreme sea level estimates. The reason for that is that if we apply those 20 different extreme value models, they agree pretty well on telling us what a 10-year event would be, because our tide gauges are relatively long, 20, 30, 40 years. So we have a pretty good idea what a 10-year storm surge event is. If we move to the more extreme events, on the bottom here, the 100-year event, we see a lot more blue popping up. Blue means that the uncertainties in our present-day estimates of extremes are roughly as large as the uncertainties of future mean sea level rise projections. And if it's purple, which also happens in some places, the estimates or the uncertainties in our extreme sea level estimates are actually larger than the estimates or the uncertainties of future sea level rise projections. Now what we can do now is we can test how these uncertainties or how sensitive risk models react to different extreme sea level data sets. What we did here is we used this Helliget model. Many of you may be familiar with the paper that was published in 2013. They developed a risk model for 136 of the largest coastal port cities and estimated present day and future risk, expressed here as annual average losses. And they used this DynasCoast extreme sea level data set. So what we did is we used their results with the DynasCoast data set, and we basically repeated the analysis. We identified cities where tide gauges were located really close to the actual area of interest, and then we have in situ observations available. So we repeated the analysis using a new extreme sea level data set that was obtained from actual observations. And then we looked at how sensitive the model would react to using these different types of extreme sea level data sets. And for present day, which in this case is 2005, because that's where the population data comes from and elevation data, we can see that differences can be pretty large. On average, across all those large cities that we analyzed, it's 30%. And it's even more if we include sea level rise, it goes up to 60%. So that shows us how sensitive our risk estimates can be to using different types of extreme sea level data sets. And the message here really is, number one, the very popular, especially at the global scale, Gumbel distribution may not be the most appropriate approach to parameterize extremes. Second, we have to acknowledge that there are uncertainties in our extreme sea level estimates. We have to put a lot of effort into improving our estimates of extreme sea levels under present day conditions. And for that, data archaeology is the stuff that Stefan is doing. I admire him for the work that he's doing, going into these archives and digitizing historic tide gauge data, which really helps us better understanding extreme sea level events. But it's also important to look into the future, and the next talk, Michalis will actually talk about how we can project storm surge statistics into the future and to incorporate that. Okay, the last slide. After talking a lot about uncertainties and how we do not know much about the future, I just want to finish with reminding you that there are concepts and paradigms in place, such as this idea of adaptation pathways, which has been very successfully implemented for the Thames 2100 project. These concepts have been specifically designed to deal with these kinds of deep uncertainties, where we have to make decisions now based on limited information. But we try to make those decisions in a way that we keep the door open to switch to a different pathway at some point in the future, if it turns out that the assumptions that we base our decisions on now are broken at some point in the future. So, and I'm very happy to see that many decision makers, policy makers are actually starting to embrace these kinds of concepts. And I finish here. Thank you very much.
Thank you, Thomas. We have time for a question. Please.
You started somewhere in your analysis of the uncertainty from these 21 models that you, as you said. And the spread you get in that analysis is really the intermodal spread.
Yeah.
You do not include in a systematic way the ensemble spread. Basically, if you run one model many times, you get actually a huge spread. It's not included in a systematic way.
No.
In that approach. What is the impact on whatever comes up?
You mean if you would include the ensemble spread?
If you include it, you have a much bigger spread.
Yeah. What we wanted to do is we wanted to focus on the intermodal uncertainty as the IPCC does with their future sea level projections. We discussed the idea. Huh?
That is not the full uncertainty.
No, we are aware of that. Actually, we are looking, I did some analysis in the paper where I included the confidence levels of fitting an individual distribution, which basically would cover the ensemble spread, and compare that to the uncertainties or the range that we get from fitting different distributions. So we have accounted for it in a way, but not systematically, as you say, and that would be an interesting next step to actually do. And for that, again, it will be incredibly helpful to have longer records available from data archaeology, from extending those reanalysis products, the hindcast products, to reduce these uncertainties that we would put on an individual distribution that we fit to the data.
Okay, thank you. We need to move on.
Our next speaker is, I'm sorry if I butcher it, Michalis, hopefully close, Global Projections of Extreme Sea Levels in View of Climate Change.
Thank you very much. Everybody misspells my name, so I will repeat. It's Michalis. So I would like to thank all the previous speakers for setting the scene. Working in a policy support institute, just to give the motivation of the work, what we know so far is that for the previous century, the rise in coastal risks was driven mostly by socioeconomic development. So we know that the population has been increasing very rapidly, and we have most of the developing taking place at the coast. So what we have seen is that in the past, we had seen more impacts, but those were mostly because of socioeconomic growth. But at the same time, as other speakers already presented, we have seen that the sea levels are rising, and the projections, they show that this is happening also with an accelerated rate. So this brings us in a world that it's going to be much different to what we have seen so far. So the previous speakers also explained how important it is that when we do these impact assessment studies, that we catch very well the spatial variations of the extreme sea levels. So what we are trying in the JRC is that we try to generate projections of extreme sea levels, but catching really all the components with projections driven by dynamic simulations. So we have probabilistic projections of sea level rise that you can see on the left. We do simulations of waves using WaveWatch 3 and driven by a CMIP5 6-member ensemble. We do simulations of tides and storm surge using FES 2014 and DFlow FM. And okay, because being a policy support institute, in the end we have to calculate also coastal impact, so we do also inundation and impact modeling. In order to have a robust reanalysis for the baseline conditions, we also, apart from the waves and the storm surge in the climate extremes, we also considered all the recorded hurricanes. So we did thousands of simulations using the best tracks, and this is the kind of results that we have. So now I'm presenting first of all the sea level rise. We can see here, I will explain the speakers because they are going to be repeated several times. We have 2050, 2100. We have two RCPs, moderate CO2 mitigation scenario and business as usual scenario. As is expected, we have projected rise almost everywhere along the world. The exception here, we have a known uplift process. We see also that changes in tides. So here we do simulations of tides considering the range of the sea level rise projections. And we take the high tide water level, which is the most relevant for the extreme events. So here are the baseline conditions. We see that there are some patterns of change. Local changes can be more important, can reach 10% of the range of the projected sea level rise. So we can see that locally they can be important, but if you take it on a regional or a global scale, the differences are minimal. For the climate extremes, we consider the combined effect of waves and storm surge. And here we have 6 GCMs, and we also do non-stationary extreme value analysis. So this is quite relevant to the previous presentation by Thomas, because the advantage of going to a non-stationary approach when we do climate change projections is that instead of having a 30-year time series, we have a 130-year time series. And then the fitting of the extreme value distribution becomes more robust. So I put the slide here because we also published a paper and we have a script that is open access, so I encourage you to go and have a look. So similar to the tides, this is a plot that shows how the climate extremes will change in the future. And we can see, for example, that in some areas, like the north of Europe, we see an increase, a consistent increase for all the years, and the RCPs. There are parts of Europe where we have parts of the world where we see a decrease, but on a regional scale, we can see that the contributions in the extreme sea levels by the climate extremes, they can exceed the 30% of the sea level rise. Another point that is important about handling the uncertainties is we have all the components as probability density functions. And this means that, for example, for the tides, in the probability density function, we have the probability that what will be the high tide water level, depending if we have spring tides or neap tides. We have the uncertainty related to simulating the tide with the ocean circulation model. We have also the uncertainty among scenarios, and similarly for the climate extremes, we have also the intermodal variability when we have a climate GCM ensemble. So all these probability density functions, they are combined in a Monte Carlo simulation, and in the end we get probabilistic projections also of the extreme sea levels. So in a way we try to handle a bit better the uncertainties. The result is the projections of the change in the extreme sea levels. So here we are seeing at the 100-year event. Of course, everything is yellow, orange, or red, depending on the time slice and the scenario. So depending on the RCP, the median is a rise of 20 to 30 centimeters, and by 2050, and 51 to 86 centimeters by the end of the century. In this plot, try to give an idea about the relative contributions of all the components, since we have all the different components together, but also how these components, they contribute to the general uncertainty. So you have here changes in tides, changes in climate extremes, contributions from Antarctica, land water, Greenland, glaciers, the steric effects. And we see here that the rising extreme sea levels, they are mostly driven by thermal expansion, the glacier contribution, Greenland and Antarctica. In terms of uncertainty, for the present, the biggest source of uncertainty are the estimations of the climate extremes. And this is related to the fact that we have an ensemble of GCMs, and we have also an ocean model which has an accuracy of about 10% in our case. But as we propagate in time and go towards the end of the century, other factors become more important in terms of the total uncertainty. This plot is also similar to the one that Thomas showed before, with the difference that we don't take specific locations, but we take regional averages. So, for example, here is RCP 4.5 for the 2050, and we see what is the contribution of the different components to the total, which is here in blue. Of course, I cannot go very deep into detail analyzing this figure, but we see, for example, that for the Mediterranean Sea, climate extremes are decreasing. In other areas, they are increasing, and we can see that these patterns, they change in time and space together with the uncertainty. So it's clear that all this will result in increasing impacts, and this has been shown also by other studies. What we see here is the change of frequency of the present-day 100-year event in 2050 and 2100. And what is important is that we see here that most part of the tropics under both RCPs, they are red, which means that the present-day 100-year event will become one-year event. And also in the Mediterranean Sea, we see a tenfold increase in frequency. And this is important because, for example, these are areas that they are relatively poorer, and they have a lower capacity to adapt compared to more advanced, richer societies. So I'm going to skip these slides, and what is important now is that if we take all the different natural hazards, because in the JRC we have groups that are working also in other natural hazards, we know that the change in climate will change the intensity and the pattern of the impacts. And this, we see the same thing for the waves. For example, we see that some areas will have more waves, some areas will have less waves. But what is important for the coastal floods is that we have sea level rise, which is an additional magnifying factor. And for example, for Europe, river floods at the moment, they are 0.4. Direct impacts from river floods account for 0.04% of the GDP, and they are projected to rise to 0.1% of GDP. Coastal floods, for the moment, they are 4 times less important, but they are projected to become 8 times more important than the river floods. So this renders coastal impacts one of the most important natural hazards in the future. So I'm going to skip these slides to allow also for some questions. What I would like to say is that all the data we produce, they become publicly available once we publish them. So feel free to have a look at the repository and also the website, and also to contact me for any questions. Thank you very much.
Yeah, we have plenty of time for questions. I might start off with one. When you construct these projections and look at the spread in the models, do you consider model skill? Do you fold that in, or do you weight each model individually, in particular for dynamic, sea level? I'm thinking about sort of El Nino, those type of things.
Well, you mean about the sea level rise projections?
Yes.
Well, these ones, actually, we got them by Svetlana Gebreyeva.
Okay.
So I think I don't know very well the details.
Okay. Are there more questions? We have a couple of minutes, or a minute or so. Back there, please.
I might have missed it, but is the change in tropical cyclone activity taken into account in your projections, given that the global climate models do not have the resolution to properly represent their ethnicity?
Yeah, that's a very good question. So basically, in this work, we try to do things that have not been done before, like including the waves, including the tropical cyclones in the reanalysis. It's true that for the future, we don't have the tropical cyclones. But what we have seen also when we're doing the reanalysis is that sometimes for example, the waves or the storms that are generated by the smooth pattern in the GCM results in a higher storm surge than the actual simulation of the tropical cyclone. So basically, since these patterns are visible in the atmospheric field of the GCM, what we make for the moment the assumption that if we have, for example, 10% increase in storm surge from the GCM, we assume that this will be 10% also with the tropical cyclones included. So it's an assumption.
There's still some uncertainty.
Yeah, of course. The right way to do it is to run synthetic tracks for the future. But then you have the problem that how do you blend with areas of the world that the tropical cyclones, they are not so important, and you have to use the forcing of the actual GCM. So it's not very easy to solve.
Okay, thank you. Let's move on to the next talk.
Next, we're going to have Tyler, who's speaking about spatial variability of coastal wetland resilience to sea level rise and the Bayesian inference.
Hello everyone, welcome to my talk. Thank you for being here. I'm going to be talking about more of the application side of sea level rise science in detecting the spatial variability of wetland resilience to sea level rise. So in the Gulf of Mexico, sea level rise contributes to a lot of wetland loss. 40% of the nation's coastal wetlands are in the Gulf of Mexico. However, 80% of coastal wetland loss is in the northern Gulf of Mexico. So there's a disproportionate amount of loss in this area versus the rest of the nation. And this is important because coastal wetlands provide sustenance and protection to the area through ecosystem services. Normally, in a closed environment, marshes are maintained through processes of sedimentation from both terrestrial and oceanic sources, but are also faced against sea level rise and erosion effects. However, there is a feedback effect through the vegetation within marshes that contributes to biomass accumulation. The main focus of most of my research is on ecosystem services, so quantifying the value of the ecosystem through provisioning and regulating services. But this requires a deep ecological understanding that links between both human actions and the services provided by the ecosystem. So this is like the broad scale breadth of my work. And as you can see, in the middle of this, where a lot of the linkages occur, is through the size of coastal wetlands. So to simplify things a bit, I'm not touching on these two portions of the model, which detail energy production and the actual valuation of the wetlands. However, I'll link some resources at the end if anyone's interested in those. So the focus here is on the landscape model, which mainly predicts the size of coastal wetlands under different scenarios. So as you can see, there's sea level rise, different geological components, the riverine input, and vegetation that all influence the size of coastal wetlands. And although I'm using a statistical model, it follows the same drivers as the processes I just described before. So similar work has previously been done on trying to quantify shoreline change in terms of these different geomorphic processes. And this was done by USCS in 2015. They used a probabilistic Bayesian network. So you could think of this, at least in terms of what I do, as the non-parametric type of analog to the continuous Bayesian inference. And again, this work mostly focused on shoreline change and not wetland loss dynamics, and therefore lacked that vegetation feedback component that's seen in coastal wetlands. However, from this data set, it lent a 5-kilometer resolution geophysical data for the entire Gulf of Mexico. So it lends very well to what I was doing. And then additional to this data set, I calculated wetland change between 1996 and 2006 prior to Katrina for each one of these points in a 2.5 kilometer buffer around each point. Again, the data for these points include these geomorphic features. So relative sea level rise is calculated, tidal range, coastal slope, and wave height. And then I calculated NDMI, which is normalized difference moisture index, to quantify vegetative productivity for the area. Normally NDVI is used for this. However, there's an interference effect in inundated wetlands, and it's been suggested that NDMI would account for that. Also, I'm adding hydrological regime as seen here by different hydrological wetland areas. And that is trying to model this riverine discharge. So we're using hydrological regime watershed areas as a proxy for riverine discharge, which is a proxy for allowances sediment input. And you can see here that both the site scale, these point data, and the regions are at vastly different spatial scales. So this lends to using the Bayesian framework, which allows you to integrate things at different spatial scales. The Bayesian framework also allows for the simulation of different uncertainties, so uncertainty at the hydrological region scale, and then uncertainty at the site scale, which is what I do for the model that I use. Also, it lends to being able to make probabilistic conclusions about the hypothesis versus conclusions about the data based on the hypothesis. So for my work, I hypothesized that sea level rise would have a positive impact on wetland loss, therefore contributing to wetland loss, which is why this is red here. And that tidal range and coastal slope would have negative effects, reducing wetland loss, and wave height would have a positive effect, increasing wetland loss. I also hypothesized that NDMI would have negative effects on wetland loss because of these vegetative feedback effects, and that the effect would be higher in lower discharge hydrological regimes as sort of a complementary effect where vegetation was complementing a lack of river discharge. So my model was a multi-level model, which is similar to, say, a mixed effect model. However, there's no variance at the hydrological regime level. After examining the data, we removed coastal slope, as it was seen to highly correlate with a lot of the other variables. And as you can see here in the model, there's two sets of covariates. There's covariates that are at the site level and covariates that are at the regime level. So any of these covariates that are in the model can be included at the site or regime level. And you can see this here as well. So essentially what I did is constructed all possible model combinations. So for example, you could have sea level rise only at the site level or only at the regime level, or you could have a combination, any type of combination between the two different levels. And then for all of the candidate models, I compared DIC and predictive posterior loss, DIC with the parameter penalty, and predictive posterior loss essentially just looking at the difference between predictions and the observed data. And I found that when plotting DIC to predictive posterior loss, they were essentially linearly related. However, as parameters increased, they diverged from each other. So from this point forward, I focused on DIC because it's penalizing highly parameterized models. So of the models, the model with relative sea level rise at the site scale and tidal range and NDMI at the regime scale was found to be the best candidate model. However, it is comparable with the next 4 candidate models, which include the same covariates, just in different combinations. The best model has relative sea level rise at the site scale, which wouldn't be quite intuitive considering the observed rates of relative sea level rise are significantly higher in the high discharge region, which includes Louisiana. However, the second model includes that regime scale relative sea level rise effect, so I compared these 2 models. So for any of these slides following, essentially the normal distributions that cross 0 would be deemed as non-significant in the model, and then distributions that are modeling the same covariate that overlap each other would also be non-significantly different from each other. So for model 86, which is the best candidate model, I found that NDMI suggested more resilience in the high river discharge region in Louisiana than in the rest of the Gulf of Mexico. However, these 2 are non-significantly different, so it's simply a suggestion. And the same result occurs for tidal range. However, it's only significant at the high river discharge regime. And as you can see within this model, or within these posteriors, that most of the uncertainty is captured by the tidal range between the 2 regions. This is in comparison to the second best candidate model, which says that relative sea level rise, well, in both cases, relative sea level rise increases wetland loss. But in this one, it varies by regime, in which the relative sea level rise contribution in the high river discharge region, Louisiana, was significantly higher than that, and the rest of the Gulf of Mexico, as expected. And that tidal range was, at the site scale, significant for both regions. NDMI also showed the same effects as previous, with wetland loss reduction, more wetland loss reduction in the high river discharge region. So in conclusion, the tidal range and relative sea level rise express different, individual different pressures on wetland loss. So in the first model, relative sea level rise was held at the site level, while tidal range varied between the 2 regimes. But in the second model, the opposite was true, with significance for both. NDMI was also seen to have, to be a significant predictor of wetland loss, a reduction of wetland loss. Did not significantly vary between the 2 regions, but there was a suggestion that there's a complementary effect, which is opposite to what I originally thought. And the usefulness of this is that NDMI, being a remotely sensed index, is easy to use over large spatial scales for vegetation productivity. I'm going to skip ahead here. So essentially, moving forward with this, the model that I used here is hosted in the Amazon cloud and can continually integrate more data. So it's checking the remote sense imagery as well as the geomorphic data for new information, and then integrating it into a decision support tool that is continually updating with new data to help with predictions for wetland loss based on these different covariates. And with that, take any questions. Thank you.
Thank you, Sanne. Quick question? I don't see any. Then in the interest of time, let's move on to the next talk. Thank you.
Thank you.
Our next speaker is going to be Timothy, talking about vertical land motion along the coast of Louisiana, integrating satellite altimetry, tide gauge, and GPS.
Need to switch to a Mac here. Just give me a second. This is where the wireless mouse would come in handy. It's all yours. Slides. I think with those two. I think so. Yeah. Make sure you use the microphone.
All right. Good morning, everyone. Let's do a test here. All right. Coastal subsidence and flooding. So it's well known that sea level rise is going to lead to increased flooding in the future. My research team has been looking at areas that are also undergoing subsidence. These are, we like to use the term canaries in the coal mine. The areas that are going down the fastest will experience flooding in the near future and might give us some clues as to how we can respond as a society to future flooding risk in areas that are not subsiding. On this map, you can see in red the areas that are experiencing a lot of subsidence with increased flood risk. Basically, there's two areas, the northern Gulf of Mexico and the eastern seaboard, the U.S. around Chesapeake Bay. So we've been looking at how we can best quantify that subsidence. Most of us have a tool that we like to use that may color our results. My favorite tool, one of them is GPS. And so we've been using GPS in the last decade and a half to measure subsidence rates in parts of the northern Gulf of Mexico and up and down the eastern seaboard. So what you can see on this slide is two important points. One is that the majority of Louisiana is very stable. It's not moving up or down a lot. But the Mississippi Delta, as most people know, is subsiding. And that subsidence rate increases southward so that at the southern end of the Delta, you reach subsidence rates of 5.5 to 6.5 millimeters a year. The other important takeaway message from our GPS results is that the subsidence rate correlates approximately with the thickness of Holocene sediments beneath the site. So in other words, we feel that most of that subsidence is due simply to compaction of that young, uncompacted Holocene section. Now we'd like to test this because there are issues with the interpretation of the GPS. For example, if we make a monument, the cement thing that the antenna sits on, if we make that monument too dense, it may well sink into the sediment, giving us a rate of subsidence that's too high. On the other hand, if we deeply anchor the monument into a deeper, higher density sediment section, we may miss compaction in the upper few meters, and hence our subsidence rate would be too low. So it's of interest to basically check or calibrate or validate the GPS results. And so that's the focus of this talk. How can we do an independent check of the GPS measured subsidence rate? The basic concept that we're going to use is as follows. It's well known that tide gauges record a combination of sea level rise and land motion. And so if we had an independent estimate of the sea level change near the tide gauge, then we could use that to back out what the land motion is. And the way we're going to get that independent measure of sea level is to use satellite radar altimetry. So here's the concept for satellite radar altimetry. I first started working with radar altimetry several decades ago, and at that time it was thought that it would be very difficult or perhaps impossible to use altimetry near the coastline because the instrument gets confused with off-nadir returns from the high relief coast. But many groups have been working diligently over the last few decades on retracking algorithms that allow you to correct for those coastal reflections and hence allow us to use radar altimetry, satellite radar altimetry, right up to the coastline. And when we can do that, we can do direct comparisons with tide gauges. So the retracking algorithm we're going to use is developed by my German colleagues on this talk. It's called STAR. It stands for Spatial Temporal Altimetry Retracking. And it basically partitions the echo, throwing away the parts that are corrupted by the land reflection. And my German colleagues have done a number of comparisons and tests with this algorithm, and the development has got to the point now where it really does seem to allow us to get right up to the coast with accurate height measurements, and it outperforms several other algorithms that are out there. Here's an example test from the Gulf of Trieste, and you can see I think it's the yellow line, it's the red line, which is the STAR algorithm, and you can see that it's got a much higher success rate, if you will, compared to many of the other conventional algorithms. So this is the algorithm that we're going to use to retrack our satellite altimetry data near the coast of the Mississippi Delta. So to reiterate the basic concept, the vertical land motion is basically the absolute sea level change minus the relative sea level change. So we're going to get the absolute sea level change from the satellite altimetry, and we're going to get the relative sea level change from the tide gauge data. It's important to remember that both tide gauges and the satellite altimetry measure several things, including ocean tides and the inverse barometer effect. And if the altimeter ground track is slightly different than the location of the tide gauge, those effects can differ somewhat. However, we can account for that by the use of models. There are other error sources, including instrumental noise, ocean wave and current effects that are not captured by the altimetry, which is a type of temporal aliasing, and residual ocean signals due to that spatial offset, basically a spatial aliasing. So those will be our major noise sources in this approach. Okay, so here's some details of the altimeter data. We're going back to the original 20 hertz signal. We do atmospheric corrections, both for dry and wet, delays, and an ionospheric correction. These are standard corrections that are applied. We use geophysical corrections to deal with things like solid earth tide and pole tide. And since we are comparing to GPS data, it's important that these geophysical corrections are consistent among the data sets. So we have to go back and do a fair amount of bookkeeping to make sure that we're doing these corrections in a consistent way. The map on the bottom shows the various ground tracks that we have from various types of satellite altimeters that have flown in the last 15 years or so. So there's a lot of data density, and the red circles show the areas where we're going to attempt to do this comparison. For tide gauges, we're taking the 6-minute water level data from NOAA, applying similar sorts of geophysical corrections, and then interpolating the tide gauge data to the altimetry data points. And that matching basically gives us an assessment of how good the data are. We can look at correlations, and where the two signals are correlated at shorter periods, it's an indication that things are working well. And if the correlation falls off, we know we have some sort of problem. We've updated our GPS analysis. This is pretty standard GPS processing. We're applying wet and dry delays and ionospheric delay corrections, again, to be consistent with the altimeter, and the same sorts of geophysical solid earth tide, pole tide, ocean loading tide are applied. We like to put uncertainty values, like most of us, and the way we're going to estimate uncertainty is a technique called the Allen variance of rate. I won't go into the details here, but basically you take a short section of data, look at the power spectrum, and then extrapolate down to the length of time series that you happen to have. And typical uncertainties for the data set that we have for this study are around 0.5 millimeter a year. Okay, so I have a few results slides. First one I'm going to talk about is at Grand Isle. Grand Isle's had a long history of tide gauge measurements and GPS measurements. The map on the upper left shows the various ground tracks and their correlations. So colors like yellow and green and blue are great. Colors like red are not so great. On the right-hand side, you can see the two time series. And then what we're really interested in is the difference in yellow. So that's altimetry minus tide gauge rate. And that number is shows a subsidence rate of 5.6 millimeters a year. For comparison, the GPS rate we have at that site is 5.9 millimeters a year. So those numbers are equivalent within uncertainty. So that's a nice confirmation that the relatively high subsidence rate we see at the southern end of the delta is likely a true thing and not some artifact of the GPS monumentation. Okay, here's some results from the Amarata Pass. This is in the Atchafalaya Delta. Again, the map on the upper left shows the correlations. The two time series are in the upper right. And the difference, which is in yellow, is the thing we're interested in. And that difference is 4.9 millimeters a year of subsidence. And again, the comparison to GPS is pretty good. GPS shows slightly higher subsidence of 5.4 millimeters a year, but those two numbers are equivalent within uncertainty. And last, we've shown results of Pilot Station on the very tip of the Bird's Foot Delta. Now, we don't have any GPS data here, but since we have both tide gauge and altimetry, we can get an estimate of subsidence anyway. And we looked at this because there were indications that this area is subsiding very fast, 27 millimeters a year. That's the highest observed subsidence rate I've seen along the Louisiana coast. One possible explanation is that it's reflecting nearby offshore oil production, but that remains to be verified. So you can look at the power spectra of the difference between the altimetry and tide gauge and get some idea of uncertainties. And basically we see two types of patterns. So at the Amarata Pass and Pilot Station sites, we see very large annual amplitudes, which we suspect is simply reflecting the annual flooding, spring flooding that occurs at these river sites. Grand Isle is not close to a river, and it instead has significant diurnal and monthly frequencies, and those are likely due to tidal model errors and the offset between the tide gauge and on our altimeter ground tracks. We've also compared our data to the gridded altimetry sea level data, and if that gridded altimetry sea level product is available widely, and if that works well, that would be much easier to use than the retracking that we're doing. Unfortunately, the tests we've done indicate somewhat higher uncertainties when we use the gridded altimeter. So we feel that retracking approach is a good way to go. Okay, summary. GPS-based subsidence rate at Grand Isle and Amarata Pass is around 5 to 6 millimeters a year. Very high subsidence rates are observed at the Bird's Foot Delta, possibly reflecting offshore oil extraction. The scatter of our time series tide gauge minus altimetry is an order of magnitude larger than the GPS displacement time series, and that's probably just due to instrumental noise and imperfect geophysical models, which allowed us to match the two approaches spatially. And finally, the large annual signals at the tide gauges at Atchafalaya Delta and Bird's Foot likely reflect spring flooding conditions. Okay, I'll stop there. Thank you.
We have time for a quick question.
I'll say it. Oh, go ahead.
I might have missed it, but when you talk about altimetry, are you using the standard altimetry product or the pre-processed post-flood altimetry?
It's pre-processed. We go back to the original waveform, so we take the 20 hertz data.
Okay, let's move on to the final talk of this session. Thank you.
All right, our last speaker of the session is going to be David. He's going to be talking about interferometric synthetic aperture radar to capture spatial variability of local land-based subsidence.
Thank you very much. So the work which I'm presenting here is together with Ben Hamilton and Brett Burns at ODU, and also with Kathleen Jones at JPL. So we have been mainly looking at the Hampton Roads region and the impact of relative sea level rise. There is a significant rate at the civil side point gauge, which we can see here on the right side. That's actually really close to the naval shipyard and the naval base which we have as well in Norfolk. This region is actually quite prone to nuanced flooding, and after New Orleans it's actually the second largest or the second largest after New Orleans. You can see this here on the left hand side or on the left hand side of the slide, where you can see after 1990 that there is a significant increase of a number of hours above 30 centimeters above the mean high water level. The reason why this is really important is strongly related to the naval base. It's the largest naval base which we have available on the East Coast. So there's a significant interest of different agencies. We have interest of the Navy, we have Army Engineer Corps, we have the USGS, NOAA, as well as NASA. In addition to local planning districts, the state of Virginia as well. So why are we really looking at subsidence? Subsidence in this area is probably really important because it's the majority of the relative sea level rise budget. You can see we get up to 2 to 3 millimeters while we have 5 millimeters total. The signal is known to be a longer wavelength signal, typically measured using continuous GPS stations. Every triangle there is one of the GPS stations which is available in that area. And the signal is assumed to be related to GIA meteor crater signal, which is closer to the eastern side of the Hampton Roads area, and also from groundwater extraction. Now, the question which you can ask yourself, is this subsidence really evenly, or is this related to the spatial distribution of our GPS stations? So the hypothesis which we put forward is that it's not going to be evenly. There is actually spatial variation. And all do that, these GPS stations have really high temporal sampling, so they're capable of giving you a really small uncertainty on the subsidence rate. Their spatial sampling is currently lacking. So we are using SAR-related data, so spaceborne SAR data, where if we can maintain, let's say, good scattering characteristics of the ground, we can achieve a 30-meter resolution or better, depending on which satellite we're using. So how does it work? SAR is we're flying over the ground, and we're actually just measuring the distance to the surface. We will fly over a second time, and in that time there could be already some change in the surface. So assume that the surface has subsidence. We fly over a second time. We measure again the distance to the surface, and what we difference is a subsidence map, or what we call an interferogram. So we can keep on doing this repeatedly, and then we can construct our history on how the subsidence is going over time, and that's what we actually have done over this area. So on the right you can see the original map which we had with GPS, and we can add in the INSAR, and now you can see there is actually quite some variation across this region, which we couldn't capture before. Now, whenever you see these maps, you also want to see the associated uncertainties, and that's where we have spent quite some time on, and I will show you these results later on. So the challenges of applying INSAR over this region, there are a couple of challenges, mainly related to the wetlands. Think about the previous talk where you saw New Orleans, where you have quite a lot of these marshes. INSAR is really difficult to apply there, mainly because you lose your consistent signal over time there. So decorrelation noise of wetlands, Norfolk is actually not too bad. There's a strong metropolitan area as well. So in those regions, we can definitely get our bright scatterers back. Noise sources, one of them We are using a spaceborne system as well, so you have a lot of ionospheric noise, tropospheric noise, and you can see here an example of a data on the right of tropospheric noise, which is just between two acquisitions, and you can see this wavy pattern going over the data, and from peak to peak we're talking about 5 centimeters of delay introduced into this image. We can do an atmospheric correction using weather models, but weather models are typically coarse. They can be up to 12 kilometers if you use an off-the-shelf model, or you can run your own model. But here we're really looking at wave patterns which are probably about 2 kilometer wavelength, spatial wavelength. So in the end, the model tracks the long wavelength trend, but can't really get rid of these high frequency noise sources. Then we also have a superposition of tides, like as was introduced in the previous talk already. We have solid earth tides, we have the marshes or the wetlands, which might be pulsating a little bit depending on the tides. We have the GIA signal, which is also superimposed, and as well anthropogenic signals could be anything from local construction sites, could be pumping, etc. So how are we going to address this? We are applying state-of-the-art or advanced time series INSAR processing only to select those pixels which preserve their scattering characteristics, so we might lose some in the wetlands. We apply a longer wavelength SAR system, mainly because the longer wavelengths are less affected by vegetation changes. And then lastly, we're looking at longer duration time series. And these longer duration time series, that's really how we get our uncertainties down. So here is just a small example of a shorter duration time series. You can see the red line is what we would estimate as being our average rate, and you can see the red shaded area as being, let's take one observation away, what would be the new rate be? So it's like our 2 sigma uncertainty, for example. So as long as we can make this time series significantly longer, you can see that whenever you would have an outlier in this time series, it wouldn't really affect anymore that much the estimated rate or the gradient of this line. So the other thing, what are the considerations for decision makers when we're talking about INSAR? Because it's not really a measurement which they use that often. INSAR is a relative measurement. It's only sensitive to the line of sight as well. So whenever we take our interferogram, we have difference than other rate maps. So we don't know what is absolute zero or what is the reference point. The other thing, the radars are side looking, typically almost looking nadirly down. So they are only sensitive for motion which is in that direction of the radar look direction. The other thing is uncertainties, and these are essential if you want to do any sort of projections, and we spent quite some time on trying to nail those down. So how are we doing that is we need to convert everything from the line of sight to the vertical. We are projecting it, but if you have more observations, you could also do a full decomposition. We integrate INSAR and GPS together to get rid of the relative sense and tie it into the geodetic framework. And lastly, we also propagate all our uncertainties. So we have our INSAR uncertainties, and given that we are tying it to the GPS, also the GPS uncertainties come into play. So here you can see our final rate map which we have. We only use data close to a GPS station, so you see all these concentric circles. Those circles are about 20 kilometer radius, and we use only INSAR data within that radius to tie it to that local GPS station, which is each individual square. So when we have overlapping concentric circles, we're going to perform, or we have performed a weighted average, and we have propagated all the uncertainties accordingly. So on the right-hand side, you can see the uncertainties, and where you have a lot of these concentric circles overlapping, you have lots of observations, and that's where you have smaller uncertainties. So let's zoom into the Norfolk area. There is a lot of spatial variation in this data set, but is it significant? That's the first question. So we can look at individual time series and see how well the rates look like. Now the A, B, and D locations, for example, A is just south of the Hampton city, but then D is the naval shipyard, or the naval base, excuse me, and you can see that those rates which you can see are the same magnitude of our uncertainties. We can't really tell that these are significant rates. But if we look at C, which is Craney Island, and that's a location where they have been dredging material and they have been throwing it up onto the land and have been loading it, you can really see that the rates are well beyond the 2 sigma level. So here you can see that you can say that the rate is significant. We have some other locations in this area, and again, it's hard to say if F and G have significant subsidence, mainly because the uncertainty is again the same magnitude as the rate. But for E, which is the naval shipyard, we believe at least there is a signal which is present. It's not, let's say, well beyond our uncertainty levels. We have been in contact with the Navy, and we have been able to relay this to local construction in the area. So what about the regional field? Can we say, is there any significant subsidence there? Here, every profile, you see the light colors represent the 2 sigma uncertainties of the INSAR, while the darker colors are the 1 sigma uncertainties. And for GPS, which are the red and the blue markers, they are always shown at 2 sigma. So you can see there is a good fit between GPS and INSAR. We don't really see strong discontinuities by using this local referencing technique. But we can see like Craney Island and the Naval Shipyard, as well as EPIS, those are significant signals in profile A, which are well beyond the uncertainty levels. So what about the future? This was all about using historic data. That data set was quite limited. Currently we have NISAR will be launched in 2021, and we also have Sentinel currently acquiring data over this area. So Sentinel has been acquiring since March 2015 consistently on a 12-day repeat. And the European Commission, as well as the ESA, is planning to support Sentinel at least till 2030. So we have a lot of data coming in over the next year. So here you can see a local subsidence map referenced to a GPS site here. You can see there's a lot of spatial variation, which is mainly related to atmosphere. So if we get to the uncertainties, you can see that the uncertainty grows with distance, and mainly close by, atmosphere doesn't really look different, but over 10 kilometers, 20 kilometers, the atmosphere looks different from your reference site. So this data is actually not really yet useful. It's too much atmospheric noise at the moment. So can we make it useful? I mean, yes, we can do a lot of image processing, and we could filter out a signal which has a certain spatial feature and is random in time. We could filter out all those signals. If we do that for this case, we still have this higher frequency feature which is present over our data. So I think for this data set, it's really, we need to wait a little bit longer until we have more data coming in. So currently we are at the 1 year marker, and we can see locally we have about 3 millimeters uncertainty, but at 25 kilometer distance we have all the atmosphere kicking in, making it about 15 millimeters. But if we project it to the future, and when more and more observations come in March 2022, we will really have small uncertainties, and that's where we're aiming at. We're developing all the techniques and getting ready for more and more data to come in. And that data should become more of a decision-making quality close to what you have or what you're used to when seeing GPS. So coming to the conclusions of the talk, insert processing in coastal areas is definitely challenging. You will need to do some advanced processing. You can reduce the atmospheric noise as well as tidal signals by adding in more data and averaging more over time. So the other key thing is to use a longer wavelength operating SAR system like NISAR, like ALOS2, which helps in these wetlands. And then we show that we could successfully combine GPS and INSAR, which is essential to get rid of the uncertainty in the longer wavelength of the INSAR data. So we use a GPS for that, and we provide a full framework where we propagate the uncertainties of both GPS and INSAR. And then lastly, by referencing it to GPS, we provide a subsidence map which is familiar to decision makers. And one key thing here is it could be the link between the ocean component as well as the land component. As long as the ocean component is related to the tide gauges, and the tide gauges are linked with local subsidence, then this could be a potential framework for integrating both components in a relative sea level rise sense. So I will take any questions if there are. Thank you.
Thank you, David. Questions?
Yeah, so your question was how we tie it to the, okay, that's a really good question. So currently we know what the rates are from GPS. We have continuous GPS time series. So the first thing which we do is we will look only to the same time period as has been observed by the INSAR data, mainly if there are any fluctuations. So from that, we estimate the rate for the GPS station. So we have the GPS rate, we have our line of sights from the INSAR. First, we have projected this all to the vertical, and then locally, around the 500-meter radius around the GPS station, we have tied, or we have offsetted our INSAR measurements to the GPS. So we have done that in these 20-kilometer radiuses around the GPS stations, because if we would go beyond that, we would be seeing too much atmospheric noise again. So we have these different concentric circles for different GPS stations, and then we actually did a weighted average in case there are overlapping concentric circles. Yeah.
Okay, thank you. I suggest that we take further questions into the coffee break. Thank you, David. So this concludes the first oral installment of this session. Please come back after the coffee break for the second leg, and then we have posters in the afternoon. So thanks again to all the speakers for the contributions and for staying on time. Enjoy your coffee break. Thank you.